We're going to determine if the series, the summation from 1 to infinity of 1 divided by n plus the square root of n converges or diverges. First, let's write out the first few terms of the series. When n equals 1, we have 1/2. When n equals 2, 1 divided by 2 plus the square root of 2. When n is equal to 3, 1 divided by 3 plus square root of 3, and when n is 4, we have 1 over 6, and so on. Now, to determine if this series converges or diverges, we're going to use the limit comparison test, and I'll abbreviate it by LCT. Here's how it works. We'll have two series, AN series and the summation of BN. Now, the only restriction is that the terms A sub n and B sub n must be positive for all n. And if the limit as n goes to infinity of an over bn is equal to L, such that L is positive and finite, then the conclusion is both series behave the same way as far as convergence or divergence. So then either the summation A sub n and summation B sub n converge, or they both diverge. So summation A sub n and B sub n diverge. Now, what's not possible here is for the AN series to converge and for BN series to diverge, and vice versa. Now, in a later video, we'll see another version of limit comparison test, but this one is used most often. So let's return to our series. Our series was summation from 1 to infinity, 1 divided by n plus square root of n. And we'll always call this series, the one we're trying to evaluate, the A sub n series. Now we need to select B sub n series in such a way that the B sub n series is known. We should know if it converges or diverges. And the second criteria, that the limit of an over bn should be a finite number that is positive. So here's how we do that. We look at the A sub n term. A sub n is 1 divided by n plus square root of n, which I'll write as n plus n to the 1/2. And we note that the highest power of n in the denominator is 1. So the highest power of n in the denominator, let's call it d, is 1, whereas the highest power of n in the numerator, let's call it n, the numerator is 1, which is n to the 0 power, so that's 0, and so d minus n is equal to 1. That is the difference in the highest powers, denominator highest power minus numerator highest power is 1, and that's the basis for the selection of our series Bn. So the Bn series will be the simplest possible series where the difference in the highest power of n in the denominator minus the numerator is 1, and the simplest such series is the harmonic series 1 over n. This is the harmonic series, and we know, of course, that this series diverges. Now let's use the limit comparison test. So we're going to take the limit as n goes to infinity of A sub n over B sub n. That is the limit n goes to infinity of 1 divided by n plus square root of n, that's the an term, over 1 over n, which is the bn term. This becomes limit as n goes to infinity of n divided by n plus square root of n, and we can divide everything by n, so that's equivalent to the limit as n approaches infinity, 1 divided by 1 plus 1 over square root of n. Now this is the only term with an n. It goes to 0, and the limit is 1. So our L is equal to 1, clearly it is finite and positive. Therefore, both series, that is the series we were looking at, 1 to infinity, 1 divided by n plus square root of n, and the series, the harmonic series, 1 to infinity, 1 over n, either both converge or both diverge. We know that this series diverges. And so our conclusion is that the series we're looking at also diverges, and this is by the limit comparison test. Now, for this series, we can also show that it diverges by using another test familiar to us, that is the integral test, and that's what I'm going to do here. It's not always the case that we can use several tests to verify the same thing, but here we're going to let f of x equal to 1 divided by x plus square root of x. Now this function is continuous. It is clearly decreasing on the interval 1 to infinity, and so we can use the integral test. If we plug in positive integer into this function, we get the nth term of our series, 1 divided by n plus square root of n. So by the integral test, all we have to do is look at the improper integral from 1 to infinity of 1 divided by x plus square root of x. If this integral converges, so does the series, and if this integral diverges, then the series does as well. Well, let's evaluate this integral. First, we have to look at the denominator and factor out square root of x. So square root of x comes out like this, and that leaves us square root of x plus 1 in parentheses. You should carefully note that if we multiply the denominator, square root of x times square root of x plus 1, we get in fact the original denominator, which is x plus square root of x. Now let's use U-substitution. Let u be square root of x plus 1. du dx is equal to 1 over 2 square root of x. So 2 times du is equal to 1 over square root of x dx. And we need one more thing, our limits of integration. When x equals to 1, u is square root of x plus 1, so that means u is equal to 2. And when x approaches infinity, u also approaches infinity. There, the integral in variable u becomes 1 over square root of x dx is 2 du, and then 1 over u in the denominator, and this is from 2 to infinity. This is equal to 2 times natural log of u evaluated from 2 to infinity. And of course from here you can see that this is 2 times limit as u goes to infinity of ln of u minus ln of 2, but the limit as u goes to infinity of ln of u, that goes to infinity. So this is approaching infinity, and the integral diverges. So the integral 1 to infinity 1 over x plus square root of x diverges. And then by the integral test, so does the series summation from 1 to infinity 1 divided by n plus square root of n. And this is by the integral test. So here we use two different tests, the limit comparison test and the integral test, to show that this series diverges. Now it's not always possible to use two different tests on the series, but in this case it was possible. For more videos, visit www.mathprepvideos.com.